Okay, so we started convolutional neural network in the previous lecture, and we learned that a convolutional neural network is a neural network. You know, we already know only feed-forward neural network. Consider a feed-forward neural network that there is one layer which is different from other layers, and this layer is a convolutional layer. And we learned that each convolutional layer has 3 stages, and each convolutional layer, three things is going to happen. One of them is convolution, the other one is detecting, and the third one is pooling. So convolution was basically in images, for example, you know, it can be in any dimensional. Convolving two signals is easily, you know, in images, you know, we can show it this way, and we had in a formal way. But assume that you have a small signal or a small picture, which we call it kernel, and we want to convolve it with our original input. So what we do is basically to compute pairwise multiplication of the pixels between these two, and then sum them up and put it here. And then we can, you know, do it over the whole picture, so we have a convolved feature. So we also learned that what's happening here is basically like making our layer sparse. In feed-forward neural network, we had this input, and we had, say, a hidden layer, and there was one link from any node in the input to any node in the hidden layer. But here you can imagine that if you have a kernel, say, of size 4, it's as if this input is, it's as if these 4 inputs are connected to one hidden unit, and then this next 4 inputs are connected here. So it's not that we have connection from any node to any node. So it's a sparse. So one property then is a sparse interaction, that we are going to get rid of many of these basically weights, or many of these connections, many of these links. In feed-forward neural network, if you have n units here and you have m units here, the number of links would be n times m. So as if you have a matrix n by m, it's a transformation which is going to be applied to your input vector and produce a hidden vector or an output vector. So the size of the matrix is n by m, and if you input n dimensional vector, the output would be m dimensional. Still here we may have m dimensional vector in the output or in the hidden layer, but since it's a sparse, we have less non-zero weights. If this size, you know, here for example we had 4. If this is k, you know, if this is n, this is m, in feed-forward we have n times m weights. Here we have k times m weights. For any nodes in the hidden unit, we have k nodes, which is basically the size of our kernel. So, and k is usually way less than n, so we have much less weights here. Okay? Another thing is parameter sharing. I explained this to you in the previous lecture, that, you know, we have a kernel. This kernel is fixed and go over the whole picture, right? The whole input image. So as if you have weights that have been shared, you know. Say I have a weight, this is another weight, this is another weight, and this is another way. Now, from these four now, I share exactly the same set of weights that I had here, because it's one kernel that goes over the whole picture. So the weight from this node now to this one would be exactly the same as this one. And to this one would be exactly the same as this one. And this one to this one would be exactly the same as this one. So we are sharing parameters in convolutional neural net. An important property for convolutional neural network is equivariance. You know, if you have two functions, f and g, and if f of g is the same as g of f, okay, so then you can say that f is equivariant to function g. You know, I have x, I apply function g on it, and then I apply function f. So it's f of g. Suppose that f of g is y. So in another scenario, I apply f on x, and then I apply g on the output. So it is g of f. G of f is also y. You know? In this case, we're going to say that f is equivalent to g. Say, for example, one of these functions is translation. The other one is summation. You know, I have 1, 2, 3, 4, 5, 6, and so on. So I pick this number, I translate it. So say, for example, I translate it by 2. So it becomes 4. Then I add 1 to it. It becomes 5. If I add 1 to this, it becomes 3. And then I translate it, it becomes 5. So f of g is the same as g of f in this case. So translation and convolution have this property. I mean, if you translate and then convolve, it's the same as you convolve and then translate. Okay? So why it's important, remember the example that we had for elephant, that we had a kernel function that we convolve that kernel function with the image of elephant, and the output was a feature map that shows edges of the original picture. Okay? So basically, it means, it happens because, you know, when I convolve this kernel function with a part of my image, you know, with a small part of my images, if there is any pattern similar to the pattern of this kernel, then I get high values there, right? And then I start to shift this kernel everywhere because we are convolving. That's the definition of convolve. So you can imagine that this pattern, which we call it edge now, this pattern is translated all over the place. You know, there's translation which applied to this pattern, and it's in every different part of this input image of elephant. Because of this property, I'm going to see this in the final result, because I'm convolving, you know, suppose that convolution is G and translation is F. So I'm computing G of F. It's is the same as F of G. It's as if I convolved this and captured that there is similarity between this pattern in my kernel and this image, and then I shift it all over the place. So I have a map of every place that there is a pattern similar to an edge. Okay? That's because of this property. Is that clear? So basically, you know, if you shift by a pixel, couple of pixels, and then convolve it, it's the same as convolve it and then shift. This is just for translation. It's not for other transformation. You know, if you do rotation, for example, it's not going to happen. If you do rescaling of the image, it's not going to happen. So by convolution, we can capture this type of feature, but we can't capture all type of features. So that was the reason that we can create a two-dimensional map of certain feature. Two-dimensional map of edges, for example. We can find the edge of the whole picture. Okay, so that was, we started with this slide that we have basically three stages. One of them was convolution, and we had two other. This one is detector stage. Remember in feed-forward neural network, do you remember that when we did backpropagation, we draw each unit in this form, and we said this part is simply summation of weighted sum of some inputs, comes here, right? We show it by A. And then there was this part Z, and Z was some nonlinear function applied to A, right? And that was, for example, a sigmoid function. This is pre-activation value, and this is after activation. And detector stage basically means applying this nonlinearity. So we have multiplication of this kernel times a part of the image and take the summation, it comes here. Then you apply a nonlinearity to it. Applying this nonlinearity is called detector stage. Okay, same as nonlinearity that we had before. So I think all the time we talked about sigmoid function as nonlinearity when we did feed-forward neural network. There are many types of nonlinearity that you can apply. In the past, sigmoid was quite common, and tangent hyperbolic function. Recently, rectified linear functions are very often used, and rectified linear have this form. So it's up to a threshold, it is 0. After threshold, it's x. So basically, this is pre-activation value, which is weighted sum of some values. Up to a threshold, the output would be 0. After that threshold, the output would be exactly the same as the value that you have here. It is very common in recent literature of neural network for many different reasons. One reason is that it sparse the network. It set many of these links to 0 and impose some sparsity to the network. And another reason is that, suppose that you are doing backpropagation, for example, you need to take derivative of this function. So derivative of this function, basically, if your value is more than this threshold, is 1. And if it's less, it is 0. So derivative of this function would be either 1 or 0. This can help a lot because, one of the big problems that people had in the literature of neural network before deep learning was a problem which is called the vanishing gradient. We have two important problems. One of them is called vanishing gradient. The other one is exploding gradient. So the reason that no one was able to train a deep network in practice was this vanishing gradient problem, because if you have a network with many layers and you want to do backpropagation, then the gradient is going to vanish after a couple of layers. It's a very small value, and it's going to eventually get vanished, and basically it doesn't help you to explore the cost function, and find the minimum. It's not the value is not really meaningful for exploration. The the cost, the objective function. So that was the main reason that people were not able to train a deep network, and all of the neural network were shallow before 2006. It was like only 2 layers, 3 layers at the maximum. In 2006 was the first time that researchers were able to train a deep network. When they did that, they were basically they get rid of this problem of backpropagation by training a network using layers of restricted Boltzmann machine, which we haven't learned in this class, but restricted Boltzmann machine is unsupervised, and it's undirected graphical model. So basically, if you have restricted Boltzmann machine has this form. When these are different random variables. This is random variable, is another random variable. And this random variable is observed, this one is hidden. So, and it's completely unsupervised. I mean, given this x, what would be the best representation for x in this? It's like, to have an idea. In PCA, we have x, and then we find another representation for x, and it's completely unsupervised. We don't use the label of the data, right? Dimensionality reduction. Imagine something like this, but it's energy-based, and we have to minimize, concept of energy between these two. So this is x. You're going to find a representation here. In the original paper of deep network, when deep network started, was that we had many layers, and that was input. So imagine that the input and this layer is a restricted Boltzmann machine, so you can compute this representation. And then assume that these 2 layers also form a restricted Boltzmann machine. Now assume that this is your observation, compute this one. Then assume that these 2 are restricted Boltzmann machine, and so on and so forth, up to the last one, which is your real output. Okay? Now you can train. You have all of these layers. Then you can assume that all of these layers is seed, initial value. And now you can fine-tune by backpropagation without getting to the problem of vanishing gradient and so on. That was 2006, up to a couple of years later, that was common structure of deep network. Now the common structure of neural network is basically old traditional structure of neural network. So they're not usually Boltzmann machine or restricted Boltzmann machine anymore. And we don't get to the problem of vanishing gradient due to different computational power that we have, and due to wise sort of nonlinearity that we can use, like rectified linear. Because in this case, gradient is either 1 or 0. There is no problem of vanishing gradient. If it's 1, or you completely get rid of that link, that path. So as if this path doesn't exist, 0. Or if it exists, the gradient is 1. So no matter how many layers you have, it's not going to be problematic anymore. So it's pretty common and pretty successful and pretty useful, this rectified linear. But it's just an example. Could be other type of nonlinearity here. And then the next stage would be pooling stage. So convolutional layer has 3 stages. Convolution, detection, and now pooling. Okay? So what is pooling? Pooling, suppose this is detector stage. Detector stage means that I applied the kernel to this input. I have this pre-activation value. Now I applied the nonlinearity to it. So this is Z now. Z is my detector stage, the output after applying nonlinearity. So after applying nonlinearity, we do pooling in convolutional network. Okay? So we do pooling. What does it mean that we do pooling? It means that we summarize the data in a way. Instead of data itself, we're going to use a summary, statistics of that data. I'm going to summarize this data by taking average of some of the nodes, by taking L2 norm of some of these nodes. Somehow I'm going to summarize this data. So these are a couple of common ways of pooling. One of them is max pooling. Max pooling, for example, is that for a number of nodes, you're going to take the max. Say, for example, I will take the maximum of this node, and this node. The maximum is 0.1. Is 1. I will take 1. And then this node, and this node, the maximum would be 1. And then this node, and this node, again, the maximum would be 1. And this node, and this node, the maximum would be 0.2. So I'm not using Z for the next layer. I do pooling before I pass it to the next layer. And by pooling, I mean that I summarize this in a way. I take statistics of the data in a way. For example, by max pooling. Max pooling is one way. It could be averaging, if I take the average of a rectangle. If I take average of these 4 units, for example, and put it here. It could be L2 norm. If I compute the L2 norm and put it here. It could be weighted average. Could be many different functions. But in general, I can summarize it. Okay? Any question here? In pooling, we may downsample at the same time that we are doing pooling. In this example, I had like 4 input, I have 4 output after pooling. I may reduce the number of outputs. I may say that, okay, I do max pooling, but for any tree, I do max pooling, and I keep this, so I don't do it for this tree. I just do it for the next tree. I skip 2 and then go for the next tree. I skip 2, next go for next tree. So I downsample. The number of units that I'm going to get here is way less than the number of units that I had at the output of Z. Okay? So this could be useful when you have input with different size. If you're doing this challenge of right whales, the size of images are not the same. So if you want to use any classifier that we learned so far, support vector machine, logistic, whatever, they need to have same length vectors, right? So, but suppose that you have a convolutional net. The input is different size, but the output of pooling could have all the same size, because you're downsampling. You can fix it, I'm just going to output this number of pixels if there's anything more. So I have a way to summarize it. I'm taking L2 norm, I'm taking the average of those. I don't report all of them, I'm going to summarize it, but always summarize it to the same length. Okay? So any insight or intuition about these 3 stages? Do you have any explanation, or it seems mysterious to you that we are doing some couple of different things? We are doing convolution, and then we apply nonlinearity. So nonlinearity is common with what we have done before for feed-forward neural network, and then we do pooling. Why we are doing this type of things? And take into consideration that this is one of the most successful structure of neural network. And many success stories that you hear is about this structure. What is magical in these 3 stages that make it successful, you think? Just intuitively, not mathematically. Sorry? It's kernel? Okay, so what's happening in this kernel? Mm-hmm. So good point. You know, one reason of success is just this stage of convolution itself, because it can capture useful features. We had an example that we can capture edges, right? Now, don't forget that we don't set this kernel ahead of time. We learn it during the process of supervised learning. You know, I have input, I have output. I'm doing classification. This is right, well, this is not. Okay? Now, learn a kernel using backpropagation, for example. These are my weights. Who knows, you know, this kernel, what this kernel is going to be. What is important to make distinction between right wheel and this wheel? Edges? Maybe. The size of eyes? Maybe. Colors? There's something which make distinction between them, right? And this thing that make distinction between these two, that I call it feature, can be efficiently learned during this process by learning set of weights which we call it kernel. You know, when we convolve a kernel to the image, we are capturing a set of features from that image. And that set of feature could be edge, could be color, could be shape, could be something, you know, about that image. But now it depends on my output. I'm going to learn a set of weights which is useful to make distinction for my classification. So that's one reason that this can be successful. So what else? You know, this sparsity is pretty important. I don't know, have you heard of this? There is a principle which is called, it's not official actually, principle. It's coined by Hasty, one of these co-authors of this book that we referred, statistical learning, elements of statistical learning. Bet on sparsity. So compare 2 methods. One of them is dense, one of them is sparse. Bet on sparsity. Without knowing anything else, I'm going to bet on sparsity and tell you that the sparse method is going to work better than the dense method. You know, in regression, say I have, you know, y minus beta transpose x. You know, we can regularize this by adding L2 norm of beta. But I can regularize it by adding L1 norm of beta, which make beta sparse. It's called lasso. And lasso has many interesting properties, you know, is sparse in a sense that it's gonna, many of these values are going to be 0 and going to just take one of these features, one of these variables. So some of these variables are important to predict my output, not all of them. I'm going to set everything else to 0. Sparsity have been very successful in many, many different areas. And you can look at the literature of machine learning, not neural network, anything else in machine learning during the last 6-7 years. And you can see many techniques based on L1 norm that you add some sort of sparsity, impose a sparsity to your method. You make your variable, in matrix space low rank. And it becomes very, successful. Besides the mathematical reason behind that, it seems that there is some philosophical reason behind this as well. Remember Razor of Occam in philosophy, right? Word is simple. The truth is sparse. If you have two different conjectures about the word, go for the one which is simple. Don't go for the one which, if two competing conjecture can explain a phenomena with the same power, we choose the one which is simple. Apparently, truth in the word is simple, is sparse. It doesn't involve many different decisions. It's much, simpler than we originally think. And when we are modeling the word using this sparsity, it seems to be better. So this philosophical notion aside, when you make it sparse, you avoid overfitting, One problem with this dense neural networks is overfitting. It's too flexible. Can fit anything. You make it restricted by making it sparse in this layer, by imposing the constraint that this weights should be the same. It's another constraint which make it restricted, less flexible. By adding this rectified linear, which is not an essential part of convolutional net, but if you apply it, it makes it sparse. By pulling and down sampling, you make it sparse. And instead of having many outputs, you reduce the number of basically outputs significantly. So we can basically restrict the flexibility of the method significantly, avoid overfitting, being able to learn with less number of data because you don't overfit easily. And when I say you don't overfit easily, in practice, the convolutional networks that people train now these days have sometimes millions of parameters, It can overfit if you don't have enough data. But compared to that dense network, just relative. Compared to a dense network, it doesn't overfit easily. So these are like intuitions and insight that you can have, which can explain the reason behind this success. So one important and interesting thing also that you can appreciate about pooling is that pooling makes your features resistance toward translation. Compare these two, and suppose that I had a small translation, This is my detector stage. I translate everything by 1 unit, This becomes 0.1, this becomes 1, and this becomes 0.2, so everything has been translated. Now look at the pooling stage. When that was my input, that was my pooling stage, I shifted everything 1 pixel, and this is my pooling stage. If you compare these two vectors, every single element of this vector is different from this one. If you compare these two vectors, only half of the elements of this vector is different from this. See, it's still, this is 1, and this is 1, this is 1, and this is 1. These two are different. The first one and the last one are different. But in this case, every single one is different from the other one. So as if it is invariant with respect to local translation, which is important in many type of detections. If you want to do handwritten digit detection, it doesn't matter if I write 1 like this, or if I write 1 like this, if it's here. If you simply convert these two to vectors and feed a classifier, logistic regression, SVM, it's not going to work, because the Euclidean distance between these two is huge. According to Euclidean distance, these two are very different images. Euclidean distance doesn't work like our perception. These two are very different. But if you can somehow be resistant or invariant toward local translation, then it's okay, this is the same as this one. And that's what's happening in pooling. Local translation doesn't change things much. There are other type of transformation that you would like to be invariant with respect to those, and it's not here. Like rotation, if I write 2 this way or if I write 2 this way, we as human being recognize it's 2, but Euclidean distance between these two is huge, and you can't recognize it in a classifier unless you do pre-processing. If you can be invariant with respect to translation, to scaling, these are useful things in some applications, not all applications. In many applications, it is useful. In some applications, it's not. I have a time series, and I would like to detect the change, when this change happened. I shouldn't be invariant with respect to translation, because I'm searching for that translation, basically. But in many applications, it's useful. Okay. So when you have these 3 stages, then it form a convolutional layer, and if you have this convolutional layer in your network, it's convolutional neural network. Okay? So you can imagine that convolutional neural network is feed-forward neural network with infinitely strong prior on weights. If you are familiar with Bayesian statistics, you know that in Bayesian statistics, you can put a prior on your parameter that you want to estimate. If I give you a set of points and tell you that, okay, I assume that they are drawn from a Gaussian, tell me what's the mean. You do maximum likelihood estimation and compute the mean, right? But if you are Bayesian, you don't do it this way. If you are Bayesian, you assume that, okay, this mean, whatever it is a parameter. And I have a prior over parameters. So it's not just a fixed value. I have some prior. Have prior means there's a distribution over theta. And now, parameter estimation means computing the posterior, giving this prior, and giving the data. But before observing the data, I have to have some prior. And my prior, for example, could be that this is Gaussian. The mean of these numbers itself is Gaussian and has a mean itself, even before I observe any data. Then I observe the data and I update my prior by computing the posterior, right? So the prior that you put on these parameters could be a weak prior, could be a strong prior, could be infinitely a strong prior. A weak prior, say for example, if I said it's Gaussian, it's a weak prior. So I assume that the mean of this parameter is here, but it's quite possible that many other values is the value of this theta. In this case, my data, my observation is going to play a big role when I have weak prior. It could be a strong prior that I strongly believe that it's somewhere here. And I give less value to a part of the space. And could be it could be infinitely a strong prior. Infinitely a strong prior that is that I put 0 on some space and then give densities to some other parts. I believe that some part of this space cannot happen I don't let it happen, no matter what the data is. This is my prior. No matter what the observation is, because we have to choose our prior before observing the data. So before I observe the data, that's my prior, means that no matter what the data is, I'm not going to let the posterior to be here. Can't be. It should be here. So you can imagine that convolutional neural network is feed-forward neural network with infinitely strong prior over weights. It means that I'm going to force some of these weights to be 0. I don't let it to be anything else. And I'm going to force some of these weights to be equal to each other. I don't let it to be anything else. So that's one way of looking at convolutional neural network. Convolutional neural network is feed-forward with a constraint, with different prior. So in practice, you can't implement it this way. It's not efficient to implement it this way. But theoretically, these two are equivalent. Okay. So some practical issues is that the input of the network is not usually just a grid of real value. In the examples that we had, it was a grid of real value. It was like an image. And it's a grid of real value. This is 2, this is 3. In practice, it could be, a colored picture, like in the challenge that you are doing, right whale challenge that you are doing. It could be colored picture, and color picture means that each of them are vector, not real value. So there is, some depth here. So basically, there is 3 possible values here. I have 3 channels for green, for blue, for red. So basically, we are acting over vectors, not over real valued. And we are convolving our kernel with these vectors. Okay? And that's the reason that if you look at the, like schematic diagram of convolutional neural network, you can see tensors here. So this is basically a tensor, not just a matrix, because it's 3-dimensional. Could be 4-dimensional, and in many implementation, it's in fact 4-dimensional. We have index for locations, and we have one index for channel. And in the 4th dimension, it's data points. We are doing this batch. I have 1,000 samples, so that 4th dimension would be my samples. Okay. And to make it clear, if it was not clear during the presentation, we may do, and we usually do, many convolutions. Not just one, not just with one set of kernel. We do it with many set of kernels, So it's not just one set of weights to this hidden unit. So you are learning different kernels. And one kernel can capture edges, the other kernel can capture colors, the other kernel can capture something else. So you have different feature sets. Okay. So I'm going to skip this part. It's not really in practice that important for you. Training would be same as training that we learned before. In practice, it's nothing new that you have forward, basically propagation and backward. You propagate errors backward and forward, the same as networks that we had before. And an important basically thing that you may want to know is that there are structures and there are algorithms of convolutional neural network that they don't learn these kernels. These kernels are weights. And we have to learn through like backpropagation, for example. We have to learn the weights, right? There are algorithms and there are papers that you can find that they don't learn these weights in the process of supervised learning. They just set it arbitrary to some random values. So I have a network, and this kernel is basically these set of weights. And instead of learning this, assume that I put it to some random values. I learned other part of weights of this network because it has some convolutional layers and it has some feed-forward layers. I'm going to learn the weights of that feed-forward layers. But for this part, I'm going to set it randomly. Does it going to work? Does it make sense to you to set it randomly? In fact, it works surprisingly well if you just set some random weights instead of learning those weights. Why is that the case? Why some random weights are going to work? Any idea? We don't have much time left, but let me just tell you quickly. We learned about PCA. In PCA, through an optimization, we are going to learn a transformation that take any image, any vector, put it in different space. And in PCA, you can prove that if you have pairwise distance between images, between data points in observation space, then you can preserve these distances in lower dimensional space. Okay? And it's optimal. Imagine instead of this vector U transformation that we compute in PCA, I just set a random vector. You can prove a very interesting bound that the pairwise distances are not going to be worse than a value which is not really that bad. Yeah, it means if you randomly project everything to lower dimensional space, it's not going to be a disaster. You can mathematically prove that pairwise distance is not going to be a disaster. If you want to have some insight about it, is that, think of PCA as some basis that you're going to learn or you're going to express your data in another space using this basis that are orthogonal. If I just pick some random basis, due to the fact that are random, in general, it's quite possible that they are almost orthogonal to each other. There's no correlation between them. And I can learn, over these random bases that somehow, not exactly, somehow are orthogonal to each other in that space because of this randomness. So it's possible to set them randomly. It's not as good as learning them. But don't forget that the most expensive part of this algorithm is finding these weights, right? And some people actually try to optimize over the structure first by setting these weights randomly, because one of our parameters is the structure of the network. How many layers do I need? How many nodes in each layer I need? So they play with these parameters with random weights. Random kernels. And when they find an optimum structure, they fix the structure, then they run an exact algorithm, to find all of those weights exactly, through the convolutional algorithm. Okay, so I think we don't have much time left. So I stop convolutional neural network here. Next week, we are going to start presentation. We have 20 minutes on Tuesday, because we have 3 presentation. In that 20 minutes, I'm going to give a very quick view of pack learning, which is just some theory of learning. And then we have a presentation.